we have the equation Ax equal to b, and we expand that equation, we can write this as a11 x1 plus a12 x2 plus a13 x3 . And so on. Okay, so we will essentially have n equations of this type. The first equation we will use in order to get, so this is, let us assume that we have gotten this equation after rearranging such that the diagonal dominance condition is met. If the diagonal dominance condition is met, then we will just go ahead and use the first equation to get x1, the second equation to get x2, and so on. So we will take all these terms on to the right hand side and divide throughout by a11. So what we get is x1 equal to b1 minus a12 x2 minus a13 x3 a1n xn divided by a11. Okay. This we can write it down as b1 minus summation j equal to 1 to n j not equal to 1 a1j xj divided by a11. Okay. This is how we have written our x1 as. Likewise we can write our x2 as b1 b2 minus summation j equal to 1 to n j not equal to 2 a 2j xj whole divided by a22, and so on. We will be able to write for each of the xi's. I am sorry, generalizing for xi, or xi is going to be written as bi. Okay. Keep in mind we are following the same pattern. When we go from x1 to x2 to x3, we change from b1 to b2 to b3 and so on. So bi minus summation from j equal to 1 to n j not equal to I. Okay, j equal to 1 to n j not equal to I, a I comma j xj, a I j times xj divided by a I. Okay, this is just the diagonal term of the ith equation. This is the right hand side of the ith equation, and to the left hand side we have taken all the non diagonal terms in the ith equation. Okay, and then we will go ahead and solve this equation in order to get a1, a1, a2, a3 up to an, and we will keep repeating this until we get the desired convergence. This equation, of course, we can also will be able to write it as bi minus summation of j equal to 1 to I minus 1 a ij xj minus summation j equal to I plus 1 to n a ij xj divided by a I. That is going to be our xi. What we will use to get xi value is all the old values for xi in the subdiagonal elements and all the new values of xi in the superdiagonal elements. So xi from the at the iteration value n, we are going to get that equal to Bi Aij xj n minus Aij xj n minus 1 represents the Gauss-Seidel method. Okay. So, the steps that we take in Gauss-Seidel method is first to see if the equations can be put in diagonally dominant form. Once the equations are put in the diagonally dominant form, decide on initial values of x0, y0 and so on and so forth for all the variables, and then run this iteration step using this equation for I equal to 1 to all the values of x that we have, and we keep doing this iteration multiple times so that we get the solution to converge to the predefined tolerance value. Okay. So, this is the Gauss-Seidel method. Okay. In Gauss iteration, we just keep the latest values of x1, x2 up to xn. In the Jacobi iteration, we do not keep only the latest value, we also keep the previous value, and we iterate based on only the previous values of x and not the most current values of x. So, the equation that we had for Gauss-Seidel, we will just change it. So, we have xi equal to bi minus summation I equal to 1 to n minus 1 j I equal to j to n minus 1 a ij xj minus summation j equal to I plus 1 to n okay. And what we had in Gauss-Seidel iteration is this had an index n, whereas this had an index n minus 1. The difference between Gauss-Seidel iteration and the Jacobi iteration is both of them have the index n minus 1, which basically means that we are not going to use the latest values for the previous variables, but we are going to use the values from the previous iteration. Okay. Or a more compact way of writing this is bi minus summation j equal to 1 j not equal to I up to n a I j x j okay. This should be I minus 1, not n minus 1. Okay. And this essentially is the Jacobi iteration. Okay. And to go back to the previous example of x minus y equal to 4 and x plus 2y equal to 1, we will write those equations as x okay. So, what we did was we started with x0 equal to 0, y0 equal to 0, we substitute the value of y0 over here and get x1 4. What we did in Gauss-Seidel method is then substitute this value of 4 in this equation, and we got 1 minus 4 divided by 2 equal to minus 1.5. But what we do in the Jacobi iteration is instead use the x0 and y0 values itself in these equations. So, we do not use the latest value, we use actually the previous value x0 in this equation, so that y1 we are going to get equal to 0.5. Now, we substitute the value of 0.5 in this equation to get the value of x, we substitute the value of 4 in this particular equation to get the value of y. Okay. So, our x2 we will get it as 4.5, or y2 that we will get is essentially going to be 1 minus 4, that is minus 3 divided by 2, and that is minus 1.5. Okay, and we keep repeating this process over and over again until we reach convergence. What we will see actually is that the conditions for convergence of Gauss-Seidel method as well as for the Jacobi iteration method remains the same, only the procedure in which we do the Gauss-Seidel method versus the procedure in which we do the Jacobi iterations are differ from each other in their details. Okay. So that is about the Gauss-Seidel iteration and the Jacobi iteration.